In this lesson today, we're going to be looking at solving systems of inequalities. Basically, what we're going to be doing is combining the idea of how to graph inequalities like we did in Chapter 2 and this idea of solving systems of equations. So we're going to combine them and talk about solving systems of inequalities. So we want to remember here that our solution to an inequality is a region. So if we're going to have a system of inequalities, then our solution is going to be a region, but it's going to be where the two regions, one from each inequality, overlap. And we'll look at that further in our first example. So we want to graph the system of inequalities, and our first one is in red, and it's negative x plus y is greater than negative 1. And in the blue, we have our second inequality, which is x plus y is greater than 3. So just like we did in Chapter 2 when we wanted to graph an inequality, we want to solve for y. So that's what we do here in this step. We rewrote our inequality and then added x to both sides in order to get y is greater than x minus 1. So looking at that inequality, we notice that our boundary line is going to be dashed because our inequality symbol is greater than. If there was an equals to included in that, then our boundary line would be solid. But because it's just greater than, it's going to be dashed. And when we look at our shading, we're going to shade above our boundary line because we want the values of x to be greater than that boundary line. And then in our blue, we have the inequality x plus y is greater than 3. Once again, we want to solve for y. So we subtract x. We're going to subtract this x from both sides. We get y is greater than negative x plus 3. And once again, we see that because of this inequality symbol being just greater than, our boundary line is going to be dashed, and the values for y are greater than that boundary line, so we want to shade above. So you have these two graphs. This red region here represents every point that is a solution to our first inequality. And then this blue region here represents our solutions, that any point within this blue region could be a solution to our second equation, which is x plus y is greater than 3. Now what you want to do is graph both of those inequalities on the same graph. So then we see that we had this red region here, which was above our red line. We have this blue region, which was above our blue line. And where it overlaps, which is this purple region here, it kind of looks like a triangle, that is our solution for the system of inequalities. So any point within this purple region here will be a solution for both of our inequalities. So let's look at an example. It says every point in the purple region where the red and blue regions intersect is a solution to the system. For example, 2 comma 2 is a solution, which is right here. It looks like that intersection point. Oh, no, I mean right up here. It's above our intersection point. So let's check that 2 in both inequalities of the system. So we take our first inequality, just rewrite it here, and plug in 2 for x and 2 for y. We get negative 2 plus 2, which is 0, is 0 greater than negative 1? No, it's not. So let's look here. I apologize. I mean that it is. I was thinking 0 is greater than 1, which isn't true, but 0 is greater than negative 1. So that statement is true. So that solution of 2 comma 2 works in our first inequality. Now let's check to see if it works in our second inequality. We have x plus y is greater than 3. That's our original second inequality. Plug in 2 for x and y. We have 2 plus 2 is greater than 3. Sure enough, 4 is greater than 3. So our point of 2, 2, which was in our purple region up here, works for both inequalities. That must mean that we have our correct region. So this is the solution for our system of inequalities. Next, we want to look at more of an applied problem, a real-world example. So in this example, it says Jenna spends at most 150 minutes a night on both math and science homework. She spends at least 60 minutes on math. Write and solve a system of inequalities to model how she allots her time for these two subjects. So, like always, we want to relate what is happening in our problem. We know that the minutes on math homework and the minutes on science homework is going to be less than or equal to 150, because at most she spent 150 minutes. So math and science added together will be less than or equal to 150. Then it also says in the second sentence, she spends at least 60 minutes on math. So we have math is greater than or equal to 60, because she spends more than 60 minutes. So once we have that relation happening, then we want to look at how to define our variables. So we're going to let m equal the minutes on math and s equal the minutes on science. From there, we can take our relation of what was happening in this problem and set up our equation. So you have s plus m, which we get here, s plus m, and that is less than or equal to 150. Okay, and we can rewrite that where we're solving for one of the variables. We're going to solve for m. So we subtract s from both sides, and we have m is less than or equal to negative s plus 150. Then for the second equation, minutes on math is greater than or equal to 60. We plug in our variable m there, so m is greater than or equal to 60. Now we have our two inequalities, which makes up our system, because the system of inequalities is just more than one inequality. So we have those two, and we want to graph them. So similar to how we did in the previous example, you want to figure out your boundary lines, which for both of these is going to be a solid line, because it includes equals to, and the shading. So looking here, you could use a graphing calculator if you wanted to figure out the shading. But it says in the first equality is less than or equal to. So we want to shade below. So the values of m are less than or equal to the boundary line. So looking at this blue region here, that would be our solution for our first inequality. Then for our second inequality is greater than or equal to, so we want to shade to the right of the second line. So this is our line of m is equal to 60, and since m is greater than or equal to 60, we want larger values for m than 60. So we're going to shade to the right, so that's the red region. Now where this blue overlaps with the red here, we see is purple. So that is our solution for both inequalities. This is our solution here in the purple for our system of inequalities. So now that we completed that example, we're going to move on to another example of solving system of inequalities. And this time, one of our inequalities includes an absolute value signs, which we did just at the end of chapter 2. So you all know how to graph both of these inequalities, and they're already solved for y, so we don't have to manipulate our inequalities at all. So the first one, y is greater than or equal to 3, is graphed here. So we think of y is equal to 3, graph that line. Since it includes a boundary line because it also equals to, we know that we have a solid line here. And we want to shade above because we want to think of values for y that are greater than 3. Then for the second one, we have y is greater than negative absolute value of x plus 2 and then plus 5. So we know that the v shape of our absolute value is going to be pointing down because of that negative out front. And then the plus 5 at the end here will bring it up 5. So that's why we're up here at 5, our vertex. And this plus 2 means that we're going to the left 2. So we have our vertex, and you could draw that v. The slope is 1. And then because our y is greater than that boundary line, we know that we shade above. And this boundary line is only a dotted line because of this just being only greater than. So if you combine them, the two on the graph, then you have this purple region representing our solution for both inequalities. It's our solution for the system of inequalities that we have. So once again, to reiterate, every point in the red region or on the solid line is a solution for this graph. So even this red line has a solution. The blue, every point in the blue region above the dashed line is a solution to our second inequality. So this dashed line is not, points on this dashed line are not solutions, only above, because it did not say equals to. And then in purple, every point in the purple region where the red and blue regions intersect is a solution of the system. For example, 4, 4 is a solution. So once again, we want to check. We just want to double check our work and make sure that we did it correctly. So we want to look for 4, 4 in our purple region. So we go over 4, up 4. Sure enough, right here is our point, and it is in the purple region. So we want to double check, plug that point into both inequalities and make sure it works. So we have 4 for y, and so we want to plug that in to our original inequality, which is y is greater than or equal to 3. So then we know 4 is greater than or equal to 3. So that makes sense. It works out. It checks. Now we want to plug in the point 4, 4 into our second inequality. So we have 4 is greater than or equal to, or just greater than, negative absolute value of 4, because our value for x was 4, plus 2, and then plus 5. So once you simplify that, 4 plus 2 is 6. The absolute value of 6 is 6. And then you have a negative 6 plus 5, which results in a negative 1. So 4 is greater than negative 1. And that is a true statement also. So then we know that this purple region here is the correct solution for our system of inequalities. Okay, what I want you to do next is to take a look at this inequality. I want you to try to solve it. If you need to go back into the, pause the video and go back to look at how to solve this inequality, the steps to solving it, then go ahead. You're more than welcome to do that. I am not going to show you in this video how to solve it, but we're going to talk about it in class the next day. So good luck.